Welcome to lecture 54 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. Myself Mukul Das from Electronics Engineering Department, IIT ISM Dhanbad. Along with me, Dr. Syed Sadiq Anwar Askari from Manipal University and Mr. Pranav Kumar from IIT ISM Dhanbad assisting me in conducting this course. Today we continue demonstration of solar cell simulation using SCAPS 1D, but today we will show you the effect of parasitic absorption on the performance of solar cell. In last lecture we have demonstrated the effect of contact material on the performance of solar cell, and in this lecture we will demonstrate how to set a user-defined absorption profile in SCAPS 1D simulator, followed by the effect of window layer absorption on the performance of thin film solar cell. We will consider the same structure of cadmium telluride based thin film solar cell. Before going to the simulation, let us discuss some expected behavior of the performance, how it varies with changing the thickness of the non-absorbing layers. So parasitic absorption, which is very useful term concerning the solar cell performance. So what is parasitic absorption? Basically, parasitic absorption in a solar cell refers to the absorption of incident light by the layers or materials which do not contribute to the photocurrent. That means the light is absorbed in some regions where charge carriers are generated, but these generated carriers cannot be separated or cannot be collected to the ends, that is to the contacts. That means this is treated as loss, because light energy is absorbed, carriers are generated, but that carriers cannot contribute to the photocurrent. So this is treated as a loss, and this loss is called parasitic loss or parasitic absorption loss. Parasitic means this absorption of these layers will not contribute to the current. But we cannot avoid these layers. Suppose you have a solar cell structure, we are mentioning absorber layer, but along with the absorber layer, other layers also we need for separation of carriers or some other issues. So for example, emitter layer is required to have a PN junction to create the force for separation of carriers. We need some buffer layers to reduce the defect states, that is passivation. We may need anti-reflection coating layers, which helps to reduce the reflectivity of the front surface. In this way, we may need some layers which are not exactly generating the effective carriers. Effective carriers in that sense, the carriers which will contribute to the photocurrent. So what is the origin of these parasitic absorptions? A solar cell typically has multiple layers, as I told just now. Say some transparent conducting oxide layers, some anti-reflection coating layers, some buffer layers. Sometimes it is called electron transport layers for organic solar cell or hole transport layer, some back reflector or back contacts. So if carriers are generated within these layers along with the active absorber layer, So carriers are generated within those layers except active absorber layer. They will not contribute to the photocurrent. So this is the origin of parasitic absorption. Now parasitic absorption mainly occurs in transparent conducting oxide. Transparent conducting oxide is generally placed at the front side. And the free carrier absorption in the doped oxide like ITO or FTO, these are actually used as a transparent conducting oxide. That means these layers are transparent to the incident light but electrically conductive. That means though we are telling these layers are very transparent, that these layers should not have any absorption, but it transparent for a particular range of wavelength of light. It cannot be, any material cannot be transparent for full range of wavelengths of solar light. So outside the transparent region, some wavelengths are incident which are outside the transparent region, that light may be absorbed by these layers. So this transparent conducting oxide layer may absorb some light and they may generate some carriers, but this will not contribute to the photocurrent. Similarly, the emitter or buffer layer. Emitter means there may be p-type absorber. For p-type absorber, emitter is n-type material. And buffer layer means sometimes we need in between these two layers, absorber layer and emitter layer, there is one thin layer to reduce the lattice mismatch or to reduce the defects are required, that is called buffer layer. So that layer may also absorb some light, may also means they will absorb, because every material has some absorption property that can be described from the NK file. NK file means N represents the real part of the refractive index of the material and K is the imaginary part of the refractive index, or it is called extinction coefficient of the material. And these N and K both are wavelength dependent. So for layers, that is window layer or emitter layer or say buffer layers, they have a specific values of N and K. So depending on the values of N and K, so they will absorb some lights and they will transmit some lights depending on the value of N and K, which are wavelength dependent. So this may be the absorption causes by these two layers also. Particularly, say if we take an example for CDS. CDS is the emitter layer for cadmium telluride based thin film solar cell, where CDT, the cadmium telluride, is the main absorber, but CDS can absorb some short wavelengths, that is blue or UV light, before it reaches to the main absorber, because the wavelength, short wavelength or short wavelength lights mainly absorbed near the shorter length. So if we draw like this, suppose you have a device like this, solar cell, this is suppose anti-reflection coating, some emitter, then absorber. So when light is incident, so low wavelength light will be absorbed near the shorter length after incident, and longer wavelength light, due to its long wavelength, they may reach to the bottom. If this is lambda 2 and this is lambda 1, so lambda 1 must be less than lambda 2. So near the emitter layer, this is suppose emitter layer, short wavelengths, that is blue portion or UV ultraviolet portion of the solar radiation mainly absorbed here. So these blue losses mainly due to the absorption in the emitter layer or some TCO layer, transparent conducting oxide layer. Long wavelength generally reach to the absorber, but short wavelength cannot reach, they may be absorbed before reaching to the absorber. Metal contacts or reflective layers, when metal generally acts as a reflector. Metal has a particular value of N and K also. So that metal or reflective layers, some incident light is absorbed in metal instead of reflecting back into the absorber, and also sometimes metal absorbs some light also, so that also may be loss. Encapsulation materials or glass, some absorb UV photons. Whenever you make a solar cell, for final packaging of the panel of the module, so some encapsulating glasses are there. If you find that the solar panels, so solar cells are in series and parallel combinations, they are embedded on some hard board, and on top there is a glass surface. That glass surface also may absorb some lights. So mechanism, what is the mechanism of parasitic absorption? When a photon is incident or absorbed in these non-active layers, electron hole pairs are generated, but they either not in the depletion region or not in the diffusion length. That is, carrier cannot get any force to be separated. Hence they recombine before collection. And the absorbed photon energy is lost as a heat. And so number of photons available to generate photocurrent in the active absorber becomes low, and thus it gives a low current. Very important thing is this wavelength dependence. Short wavelength loss, that is blue or UV losses, this is due to the parasitic absorption in buffer layers, say CDS in case of CDT, SNO2, TiO2, these type of materials generally responsible for absorbing the short wavelengths. And long wavelength loss, that is infrared or some higher wavelength of the visible range, is due to free carrier absorption in TCO and back reflector metals. TCO, that is transparent conducting oxide layer, they also sometimes absorb some long wavelength and they generate some free carriers, but they cannot be separated. And mid-range absorption, ideally this should be harvested, that is, should be converted properly to the carriers and the photocurrent, but parasitics in transport layers can still cause some losses. So transport layers, there is a whole transport layer, electron transport layer, they generally absorb some mid-range wavelengths. And strategies to minimize parasitic absorption, how can you reduce this? First of all, you have to reduce the thickness of these non-active layers, say buffer layers or transport layers, and the band gap of the material should be high, and band gap high means generally they will be transparent to the visible range. So first of all, making the ultra thin layers of these TCO, buffer layers, emitter layers is required. Replacing emitter or window layer with a wide band gap alternatives, say zinc magnesium oxide, zinc doped magnesium oxide, zinc sulfide, TiO2, etc. They have very high band gap, so they can be used as a emitter layer or window layer. Engineering of highly transparent TCOs with low free carrier absorption, that is also important, because TCO is responsible for free carrier absorption. So if you choose a TCO material in such a way that it has very low absorption capability for free carrier absorption, this can be used. Application of nanostructured back reflectors, this is also very recent trends. In the back side, if you have a array of nanorods or some other nanostructures, say nanopyramids like this, so the light which is reaching at the back, they may reflect it back and they may be reabsorbed by the material, by the absorber layer. So you can enhance the absorption of light. And development of selective contacts that are transparent to most of the spectrum. So contacts should be also selective and transparent. So in summary, we can say the parasitic absorption, it mainly results in reduction of photocurrent, quantum efficiency, in a particular wavelength range where the non-absorbing layers are absorbed. Thus, overall efficiency obviously would be reduced, and it also increases the heat losses. And if heat is there, so if it becomes panels becomes hot, so other effects will also come. So you have seen that effect of temperature on the performance also. So this is the important is in SCAPS 1D simulation, there are some default values of absorption profile. So you can take that and absorption from the library, that is NK file, but you can also define your desired absorption. That is, you can define the NK file. That will be shown through simulation how it can be included. And the front surface texturing effect, that is very important. You know, in a crystalline solar cell structure, we have shown you that the front surface is, instead of planar surface, some textured surface is there. So, and in the textured surface, all layers are in textured format, so emitter and absorber, whatever. So how can you include the effect of this texturing? Because only NK file of this material will not give you the effect of texturing. How can it be done? So the texturing effect can be included by an equivalent NK file, that is from other simulator like COMSOL or numerical. You have to obtain the effective NK value of this textured surface, and then that effective NK value, there is wavelength dependent NK, that is NK and wavelength, there is a tabular format. You can use that NK file, effective NK file in the simulation, then you can get the effect of texturing. Otherwise, no way to include the effect of textures in a SCAP 1D. So the simulation will be demonstrated by Said Anwar Askari.
We know that the absorption file of the absorber layer and as well as the window layer, that is important, right? Why it is important? Because if we have a very high absorption coefficient of the window layer at a visible range, then the most of the electron will be absorbed in the window layer. So that's why majorly we want to get absorption in the absorber layer. So for any new material, how we can define the user-defined absorption property for the simulation in the SCAPS. So in this session, we will discuss about this concept in more detail. So where we have to define the user-defined layer. So let us go to the set problems, and then we can see here the CDT is a major absorber layer. So by clicking on the CDT, this is the electrical property, and the bottom one you will find the optical property, that is the absorption property of that material. So here the two options for the selection of the absorption property, one from the file and another from the model. So more close to the experimental one, that is we can select from the user defined file, and that user defined file either you can get from any reported paper, or if you are working on the experiments, right, then from there you can get a material property, the absorption property, and from that you can generate your own absorption file for the simulation purpose. So how we can do that and where we can do that? So first try to understand where we have to port in the program. So in this position you can port your own user defined absorption file here, from not from the model, from the file. So by clicking, by choosing the from the file, then we can click on the set absorption file. So this is the absorption folder where all the absorption file is preloaded, or you can design your own absorption file in this position. So how we can do that? So here we can go to the SCAPS folder, right? So for that you can directly go to the SCAPS folder. So this is a SCAPS folder, right? So for that you can go back to the again SCAPS folder. Here many files are there, and by clicking on the absorption file you can find that absorption.abs file. Now you can choose any ABS file, like here we have selected amorphous silicon absorption file, and you can copy it and you can paste there, right? Continue. right, because we don't have any access for the access of this folder. So that's why I am able to paste it, right. But if you have access of C drive, then you can easily access that one. But if you want to change by pasting there, right, here right now I am opening. So this is a notepad where we can open that one. So here by clicking OK, you can open the absorption file. Here the two columns are there. In the first column, that is the lambda, that is the wavelength. The wavelength is defined unit will be in the nanometer. So always remember, when you will define the user defined absorption file, then you have to define lambda in terms of the nanometer, right. And in the next column you will find the alpha, that is the absorption coefficient. So alpha unit is per meter, right. So whenever you are defining new material, then alpha will you have to choose in the per meter in this situation. In the top of the two line, that is the comment line, right. So these are the comment lines you can choose. So whenever you will design your new file, so one thing is very important there. First, you should write from where you have taken this material property, right. So otherwise what happen, if we will report in the paper, then at that time you will forget from where I have taken this absorption file data. Either you can type the name of the journal and detail about the journal, and if you have your own experimental data, then you have to write down in which date of the experiment data you have collected. Like for the multiple dates, you have the multiple samples, and then each sample have different absorption file. So to get the reference of this absorption file, it's better to mention either from which date experiment you have taken this absorption data, or if you have taken from the journals, then you can clearly mention the detail about the journal in the comment, right. That is very important step to define the user defined absorption file. Otherwise what happened, at the time of writing the journals or articles or the thesis, it is very difficult for you to get the reference for this data. Okay, so this is one important point. Like here, the 2-3 lines are the comment lines, and the next, this is the lambda in the nanometer, and this side is the alpha in the per meter, right. And then all the range whatever you have defined, then you have to define there. But one another point where you will last, so what will the last value of the nanometer? Suppose you have a limited data from the paper, right, that is only in the range where the absorption will be there. So if the last data have the high absorption value, so for the further value they will consider the same value in the interpolation, either extrapolation or that will be there, right. They will extrapolate that first and last value. So if we have reported that is the last value at 700 nanometer, and then whatever you have set at the value, that is the spectrum, the solar spectrum in the range of 900 nanometer also. So for the 900 nanometer, they will get the alpha by extrapolating the last value, that is 700 nanometer. So that is important, that try to close down the absorption data is the lowest value of the absorption, that is in the order of -1 you can choose. So in that way there is no overestimation of the absorption data. Otherwise what happen, you may get the overestimation of the absorption within the absorber layer or whatever the layer you have selected for your user defined absorption file, right. So that is another important property. Now by editing in the same folder, like here I will try to edit this one, right. I have deleted down, but I cannot save, I cannot modify this data in this folder, right. Otherwise what happen, they will give you the save in the .txt file. So it is a better practice that just try to copy this data, just try to copy any of the file, and you can go outside the program folder, right. You can go outside the program folder, you can choose any folder, then you can paste it, right. Then you can paste it, and then you can open this one in outside the C drive and open this one, and here you can change or modify the data, right? And here you can change and modify this data. Let us choose, I have modified this data. So now in this position you can easily save the data and modify the data which is outside the C drive, right? So best practice, copy a use already predefined .abs file and paste in outside the C drive and then modify that data according to your data, and you will also set in the comment file the reference. And after completion of the modification, right, like here I have modified that one. So let us see, this modification is that amorphous silicon underscore modified or test, right here. Now we can choose this one and let us, I can try to paste in the main file in the C drive. So you can go to the C drive and the program file, and within the program file you find the SCAPS folder, and the SCAPS folder there is the absorption file, and try to paste there, right, continue. So because I don't have access for this folder, so that's, so this access restriction mainly due to the laptop restriction. So if you have your own laptop, then you can easily copy and paste in this folder, right? So then in that way you can define your own absorption file, and this absorption file you can use for any layer, right? Like here I can choose this absorption file for the define for setting in the window layer. So in that way you can define your own user defined absorption file, and you can use this user defined absorption file for your simulation, and that simulation will more close to the practical one, right? So we have completed how we can define the user defined absorption file, what are the parameters or constraint we have to consider at the time of defining the absorption file. So first the two column will be there. In the left side we have the wavelength, in the right side we have the absorption coefficient alpha, and unit of the wavelength is in nanometer, and unit of alpha will be in the per meter, right? And on top of that, in the comment will be there. In the comment you can define the reference of your data, and then you can save this .abs file from outside the C drive, and you can paste within a C drive, that is in the SCAPS folder and the absorption folder. So in that way we can define the user defined absorption file. Thank you. Hello everyone. So in this session we will discuss about the effect of band offset, that is the band discontinuity in between the absorber layer and the window layer, right? So how we can design, how we can choose that one? So for that let us start to defining the problems. So by set problems we can define the new problems. So here we can choose the, so now I am deleting the additional layer, remove layer. So first you have to set the problems. So for that we can load the new problem. So here we have selected the CDT based solar cell. So this is your CDT CDS based solar cell, and then within that we have to define the band offset in between the absorber layer and the window layer. So for that we can choose the CDS layer, this is the window layer, and its work function. Here we have selected the electron affinity, and we can optimize this electron affinity. Here we have selected the 4 electron volt at its electron affinity. Now we will see how it will affect the performance on the solar cell. So by choosing or by varying this electron affinity we can try to understand this concept. So for that again we have to go for the batch simulation. So here we can go for the batch setup, and which parameter we have to select? We know that the CDS is the window layer, so we have selected the CDS layer, and which parameter within a CDS layer we have to select? That is the electron affinity. So electron affinity will decide the band discontinuity between the window layer and the absorber layer, that is the CDT. So earlier the well defined its electron affinity is 4 electron volt. Now we will set the multiple parameter for the electron affinity. Now we will choose its value. So how we can do that? So here we can choose better from the variation. So we can start the variation from the 3.6 to the 4.4, right, or 3.7 to 4.4. So we have started the electron affinity of the window layer from 3.7 to the 4.4. How many value will be there? So that will be 8 value, right? So 7, 8, 9, 10, 1, 2, 3, 4. So that will be the 8 value. So we have selected the variation of the electron affinity from 3.7 to 4.4 electron volt, and then we can start the simulation, right? So for that again we have to set the problem. For the light illumination we have to check light is already given there, and then we can check that what is the incremental value will be there for the, and the range of the voltage here we have selected 1 volt maximum, and then the stepping we have selected the 1 millivolt, right? And next we have to choose its batch setup. So batch setup already we have selected, and what are the parameter we have to record? So these are the parameter we can record there. So other parameter we can also select from the general property or from the energy band property, that is electric field. So this already we have selected in the bottom. Now we have completed all the record setup, and before starting the record setup please clear all the previous simulation data. So in that way we have completed that one, and then we will started the calculate recorder. Okay, so now the simulation has been started. So now we have completed the simulation. So let us see what will be the effect of the band offset, right? So for that you can go to the recorder. So by clicking on the recorder, right, by clicking on the recorder you can find what are the parameters will be there. Okay, so what is the variation in the efficiency will be there? So if the work function difference between the window layer and absorber layer is high, in that way there will be a reduction in the efficiency. Now you can see that what is the value of the efficiency for the different work function of the absorber for the window layer, right? Here the window layer, the CDS we have selected. So at the very lower work function you will find the efficiency will be the highest, that is 16%. But by increasing the electron affinity of that window layer, we can find that there is a reduction in the efficiency. Basically this will due to the creation of the barrier, right? So at the lower work function the band discontinuity will be different, and at the higher work function the band discontinuity will be changes. Now we can see that this electron affinity at 3.7 electron volt the efficiency is 16%, but at the 4.4 electron volt electron affinity you will find the efficiency drop down to 11.4%. So what is the reason behind that? So we can see the reason first, which parameter will majorly affected. For the VOC is affected from 870 millivolt to, so there is an increment in the VOC for that one. So which one is majorly affected? The JSC. JSC is 24.2% to 23.9%. There is no major effect on the JSC. Now the major variation in the fill factor. See what happened, due to the reduction, due to the change in the band offset, there will be a barrier is created, and due to that there is a series resistance change, right? So it will increase the series resistance, due to that there is a major reduction in the fill factor. So this will be a major reason for increasing the electron affinity of the absorber layer, the window layer, right? So now again let us see the interface recombination. There is no much change in the interface recombination. Left contact, not much variation is there, right? The left contact is also affected by the increment in the work function, right? And let us see its now. This is the major issue, right? Now we can visualize in more detail. So for the lower work function, right, and the lower electron affinity and higher electron affinity, you will find the different electric field, right? So the electric field variation you can see from this structure, right? Okay. Now this is the energy band. Now this type of notch you can observe for the higher work function, a higher electron affinity of this material. You can see more closely there. Nice. So let us see, we can zoom the layer so we can visualize in more clear way. So this one here you can find the notch in the conduction band. So this notch is responsible for the change in the fill factor, and this will majorly affect the efficiency. So in this way we have seen how there is a variation in the efficiency due to the change in the electron affinity of the window layer. So in that way we can optimize the different parameters of the all the layers. Like here the window layer electron affinity is very important, so that's why we work on that, right? So I hope you enjoyed the session.
You have learned how to include the user-defined NK file in SCAPS 1D simulation. So the texturing effect also can be included. You can try to include the effect of texturing. Obviously the performance will be boosted up. Thank you.